Yeah.
Like you pick up your phone, what makes the screen light up? What makes the metal casing feel so solid? It's easy to take for granted, but when you start thinking about it, like fundamentally, it gets seriously mind-bending.
It really does. And that's exactly where we're headed today. We're diving deep into a concept that's just absolutely central to understanding all of that.
Yeah.
How those tiny regions of space where electrons hang out, what we call quantum orbitals, aren't actually just stuck to single atoms inside a material.
Exactly. Yeah, we've got a whole bunch of fascinating material here that digs into this, from the basics all the way to some really, really exciting applications.
Right.
Our mission today basically is to unpack why this extension of electron orbitals is just so crucial. We're talking the underlying reason metals conduct electricity, how something like superconductivity even happens, and really the foundation for a lot of future tech.
And think about that picture you probably have in your head, the atom, like a mini solar system, electrons zipping around.
Yeah, the classic model.
That's a decent starting point, I guess, but the quantum reality inside actual materials, it's way more connected, way more dynamic.
And just to grab your attention right off the bat, think about this. Those electrons making your phone screen glow right now, they aren't just orbiting their own little atoms. They're in this kind of quantum community, a shared existence that makes the whole thing work. Okay, so let's really dig into this.
Okay, so let's start with an atom all by itself, isolated. Its electrons occupy specific quantum states. These are the atomic orbitals, the SPDF shapes.
Right, those diagrams you see in textbooks with the different shapes and lobes.
Exactly. Those describe the probability, basically, of finding an electron somewhere around the nucleus.
Okay, standard stuff. But what happens when atoms get close? When they form molecules or, solid materials, that's where it changes, right?
That's precisely when things get interesting. When atoms interact, their atomic orbitals kind of merge or combine. It's a process called the linear combination of atomic orbitals, LCAO for short.
LCAO, okay.
And this creates new orbitals that actually span across multiple atoms. These are molecular orbitals.
Ah, so they're shared now.
They're shared. And you get two main types. Bonding orbitals, which are lower in energy and kind of glue the molecule together.
Right.
And anti-bonding orbitals, which are higher energy and, well, they tend to push things apart if electrons go in there. You can kind of picture it like waves overlapping.
How so?
Well, if waves reinforce each other, you get a bigger wave, right? That's like bonding. If they cancel out, you get less wave or nothing. That's like anti-bonding.
Okay, I think I can visualize that. So the electrons aren't just stuck to one atom anymore. They're in these shared spaces between atoms and a molecule.
Yeah.
But how does that scale up? Like from a couple of atoms to the trillions and trillions in a piece of metal?
Great question. That's where we move from molecular orbitals to something even bigger, extended wave functions. In materials with repeating structures, like metals or semiconductors, these quantum wave functions don't just cover a few neighbors. They stretch out across the entire crystal structure, the whole repeating pattern. We often call these block states.
Block states. So they're like really spread out.
Extremely spread out. This idea of delocalization, that electrons aren't locked down to one spot, is maybe the fundamental difference between lonely atoms and real materials. It's this community aspect that gives rise to so many properties.
Okay, so this interaction, this delocalization in solids, it leads to something called energy bands, right? Can you unpack that a bit?
Absolutely. Imagine you have just a huge number of atoms in a crystal. All those individual atomic energy levels, they start to influence each other. It's like, think of a single guitar string vibrating at a certain pitch. Now imagine millions of identical strings all coupled together. You don't just hear one pitch anymore. You've got a whole range, a band of frequencies. Okay. So the individual energy levels sort of smear out.
Exactly. They broaden into these continuous ranges or bands of allowed energy states for electrons. That's what we call energy bands.
And the key ones are the valence band and the conduction band, I think. What's the deal with those two?
Yeah, those are crucial. The valence band is generally the highest band that's filled up with electrons, especially at low temperatures. It's where the electrons normally hang out.
Okay.
The conduction band is the next band up in energy. Now, if electrons can get into the conduction band, or if it overlaps with the valence band, then those electrons are pretty much free to move throughout the material.
Okay. So that's where the interesting stuff happens for electricity and things. How does this band structure tell us if something's a conductor or maybe an insulator?
It all comes down to the relationship between that valence band and conduction band. Specifically, do they overlap? And if not, how big is the energy gap between them?
In conductors metals, basically the valence and conduction bands either overlap, meaning there's no gap, or the conduction band is already partially filled.
So electrons can easily move around?
Instantly. There are always available energy states for them to jump into and move. That's why metals conduct electricity so well. Lots of mobile electrons ready to go.
Makes sense, like an open highway for electrons. So insulators must be the opposite then.
Exactly. In insulators, there's a big energy gap between the valence band, which is completely full, and the conduction band, which is completely empty.
Too big to jump across easily.
Way too big under normal circumstances. An electron would need a huge jolt of energy to make that leap. So effectively, no electrons can move into the conduction band to carry current. They're stuck.
And semiconductors, like silicon, they're somewhere in the middle.
Precisely. Semiconductors have a band gap, but it's smaller, more manageable than in insulators. At room temperature, just the thermal energy kicking around is enough for some electrons to hop across this smaller gap into the conduction band. That allows for some conductivity, but not like a metal.
And we can mess with that conductivity, right? Doping and stuff.
Exactly. That's the magic. By adding tiny amounts of impurities doping, or by applying an electric field, we can control how many electrons get into the conduction band, or how many holes, like missing electrons, are in the valence band.
Which is how transistors work, like tiny switches.
That's the absolute core principle of a transistor, controlling that flow of charge carriers. And it all hinges on this idea. Electron delocalization creates these bands, and the gap between them determines everything.
Wow. Okay. So we've talked about delocalization generally, but the type of bonding in the material must matter too, right? Like covalent bonds. The sources mention graphene and diamond.
Oh, absolutely. Bonding type is critical. Take covalent bonds. In graphene, each carbon atom uses sput hybridization.
Right. Flat sheets.
Right. It forms strong bonds in that 2D sheet, but it leaves one orbital sticking out. These parorbitals overlap sideways all across the sheet, creating a huge network of delocalized pi electrons. These electrons can zip across the entire graphene sheet almost unimpeded. That's why graphene is such an amazing conductor.
Okay, so massive delocalization there. But diamond also has covalent bonds, spy hybridization, and it's famously an insulator. Why the difference?
Good question. In diamond, the SPA hybridization means all the valence electrons form very strong, very localized sigma bonds in this rigid 3D structure.
So no leftover electrons to roam around.
Pretty much. The electrons are shared between specific atoms, yes, so there's some extension of the wave function, but they're tightly locked into those bonds. They don't form those wide delocalized bands needed for easy conduction like the electrons in graphene do.
Okay. So it's not just if they delocalize, but how and how much and what kind of bands that creates.
Precisely. The nature and extent of the delocalization is key.
Got it. Now, what about metallic bonding? We always hear about the sea of electrons. How does that fit with these extended quantum orbitals?
The sea of electrons is actually a pretty good intuitive picture for what's happening with these extended orbitals in metals. The valence electrons in a metal aren't strongly tied to any single atom.
They're just swimming around.
In a sense, yes. They're quantum wave functions, the Bloch states we mentioned, spread out over countless atoms. They form this collective sea.
And that directly leads to conductivity.
Directly. Because they're already delocalized and mobile, they can easily respond to an electric field and flow as current. And it also explains other metal properties, like malleability.
How so?
Well, because the electrons form this collective sea, the bonds aren't rigidly fixed between specific atom pairs, like in, say, diamond. If you push the atoms around, bend the metal, the electron sea just kind of flows and readjusts. The atoms slide past each other, but the overall metallic bonding holds. The material deforms instead of shattering.
Right, the glue isn't brittle. That makes sense. So this delocalization is just fundamental to being a metal. Okay, let's shift gears to something even wilder. Superconductivity. The sources call it an extreme example of delocalization. What's going on there?
Superconductivity is, well, it's amazing. It really takes delocalization to a whole new level. What happens is, at very low temperatures, electrons in these materials actually pair up.
Pair up. Electrons usually repel each other.
They do. But in superconductors, there's a subtle interaction involving the vibrations of the crystal lattice that allows them to form these bound pairs, called Cooper pairs.
Okay, Cooper pairs, then what?
Then the truly mind-bending part happens. All these Cooper pairs condense into a single, unified quantum state, a macroscopic quantum scale.
Macroscopic, like covering the whole piece of material.
The entire piece. Essentially, the quantum wave functions of all these paired electrons become phase-locked, coherent, and extend throughout the whole superconductor. It's like one giant shared quantum wave function for all those pairs.
Wow.
And that state is what allows electricity to flow with absolutely zero resistance. The paired electrons, in this highly delocalized, coherent state, move collectively without scattering off anything. No energy loss.
Zero resistance, just incredible. That really is an extreme form of delocalization. Okay, let's bring this back to some functional materials we use. Semiconductors, like silicon, we mentioned transistors.
Yes. So in silicon, you've got that crucial valence band, conduction band, and that manageable band gap. By doping it, adding impurities.
Right, controlling the charge carriers.
Exactly. You control the number of electrons available in the conduction band or the number of holes missing electrons in the valence band. A transistor uses an electric field from the gate voltage to control the ease with which these carriers can flow between the source and drain terminals.
So it's switching the flow on and off.
Precisely. It's controlling the movement of charge carriers that exist in these delocalized band states. The whole operation relies on electrons being able to move between these extended states formed by the interacting orbitals.
And graphene comes up again here too, not just for its bonding, but as a functional material itself.
Definitely. That massive delocalization of its electrons across the whole sheet gives it incredible properties, like electrons moving through it super fast, high electron mobility.
Which is exciting for electronics.
Hugely exciting. People are thinking about faster transistors, transparent conductive films, all sorts of things. It's way more than just a flat sheet of carbon. It's this unique electronic system born from extreme orbital extension.
And what about organic conductors, these conjugated polymers? How does delocalization work there?
Right, so these are often long-chain molecules with alternating single and double bonds. That pattern is called conjugation.
Okay.
Similar to graphene, this conjugation allows the electrons from the double bonds to become delocalized, not just stuck in one double bond, but able to move along the chain.
So charge can move along the polymer.
Exactly. It allows charge transport. Now, the conductivity usually isn't as high as copper or something, but the big advantage is these materials can be flexible, maybe even transparent, lightweight. Opens doors for things like printable or flexible electronics.
Again, all down to those electrons not being stuck in one place. Okay, let's zoom back in a bit. We keep talking about wave function overlap. When atoms first come together, what's physically happening with those electron clouds?
Yeah, so imagine two atoms approaching. Their electron clouds, described by those wave functions, start to physically overlap in space.
Okay.
This overlap is the absolute requirement for forming chemical bonds, whether it's molecular orbitals or the extended states in solids. The interaction during overlap usually leads to lower energy for bonding states, which is why bonds form in the first place. Generally, the more they overlap, the stronger the interaction.
And you mentioned hybridization earlier, like spending diamond. How does that fit into the overlap picture? Is it something that happens before overlap?
Hybridization is more like a mathematical mixing of the atomic orbitals on a single atom to prepare them for better bonding. Like carbon's s and p orbitals mix to form, say, 4 equivalent speed orbitals pointing towards the corners of a tetrahedron.
Ah, okay. So the atom rearranges its orbitals internally.
Kind of, yeah. These new hybrid orbitals often have shapes that allow for better, stronger overlap with orbitals from neighboring atoms when the bonds actually form. So it facilitates that crucial wave function overlap that leads to bonding and, in solids, to the formation of energy bands.
Okay, so we have molecular orbitals for molecules and these block functions for solids. The key difference is just the scale and the repetition.
That's the main thing. Molecular orbitals are localized to that specific molecule, a finite number of atoms. Block functions, because they exist in a repeating crystal lattice, extend ideally over the entire crystal. They have this property linked to the crystal's periodicity, this wave vector k, that reflects how the electron wave propagates through that repeating structure.
Right, the whole crystal aspect. Okay, let's reinforce this band formation idea. Atomic levels becoming bands. How does that directly impact how easily electrons can move? Their mobility.
So you bring many atoms together, their identical energy levels start to interact because of the orbital overlap. This interaction forces the levels to split slightly.
Okay.
With a huge number of atoms, you get a huge number of these split levels, all incredibly close together in energy. So close, they form what looks like a continuous band.
Valence and conduction bands.
Exactly. Now, electron mobility depends heavily on this structure. In a semiconductor, an electron has to get enough energy to jump the gap into the conduction band. Once it's there, it can move through the delocalized block states. How easily it moves depends on the exact shape of that conduction band, how the energy changes with momentum k.
So the band structure itself dictates how mobile they are once excited.
Yes, absolutely. It determines the electron's effective mass within the crystal, how readily it accelerates in an electric field. It's all encoded in that EK relationship.
And for metals, since the conduction band is already partly full.
Right, there's no gap to jump for many electrons. They are already in those mobile, delocalized states. An electric field can immediately give them a little extra energy and momentum, and they start flowing as current. Their mobility is inherent because they're already in that conduction sea.
Okay, let's dive deeper one more time on that electron sea in metals. We've got conductivity, malleability.
Oh.
What about their shininess, that metallic luster? How does the electron sea explain that?
The reflectivity. That also comes directly from the free electrons. When light, which is an electromagnetic wave, hits the metal surface, its oscillating electric field interacts very strongly with that sea of mobile electrons. The electrons oscillate in response to the light wave.
And they re-radiate the light.
Precisely. They absorb the light energy and almost instantly re-emit it as photons of the same frequency. We perceive this re-emission as reflection. That's why metals are shiny. Insulators without free electrons tend to absorb or transmit light instead.
Fascinating. Okay, and back to graphene and organics with the systems. What makes electrons specifically suited for this delocalization compared to these sigma bonds?
Well, sigma bonds are formed by direct head-on overlap of orbitals, usually along the axis connecting two atoms. They're strong and typically quite localized between those two atoms. Pi bonds, however, are formed by the sideways overlap of orbitals above and below the plane of the sigma bonds. When you have conjugation, that alternating single-double bond pattern, these orbitals can overlap sideways with neighbors on both sides. This creates an extended pathway, a sort of electronic highway, along the chain or across the sheet, where these electrons can move much more freely than the sigma electrons.
So the sideways overlap is key for creating that extended network.
Exactly. It allows for that extensive delocalization. And in graphene, it's the ultimate example. The entire sheet is one conjugated system. You mentioned those Dirac electrons.
Yeah, massless electrons.
Effectively massless, yes. Their energy is directly proportional to their momentum, like photons, which is very unusual for electrons in a material. It's a direct result of that specific honeycomb lattice and the way the orbitals create these extended wave functions across it.
Amazing. Okay, so we've seen conductors, semiconductors, organics. Let's revisit the exotic stuff. Superconductors, macroscopic quantum state, Cooper pairs, zero resistance. What about topological insulators again? How is orbital delocalization key there?
Right. Topological insulators are super interesting. In the bulk, inside the material, they are insulators. The orbitals hybridize in a way that creates a band gap, just like a normal insulator. Electrons are fairly localized.
But the surface is different.
Totally different. Because of complex effects involving how electron spin interacts with its motion, spin-orbit coupling, and the overall symmetry of the crystal, the electronic structure has to change at the surface or edge.
How does it change?
It forces the existence of states within the bulk band gap, but these states are spatially localized at the surface. And crucially, the electrons in these surface states are delocalized along the surface.
So they can conduct, but only on the surface.
Exactly. And these states are topologically protected, meaning they're incredibly robust against defects or impurities on the surface. It's a unique form of delocalization that's confined to the boundary, arising from the quantum mechanics of the orbitals and the bulk.
It's just wild how diverse the outcomes can be based on how these orbitals interact. So stepping back, what's the big picture message about quantum mechanics when we look at real materials, not just isolated atoms?
The really profound takeaway is that electrons in condensed matter in solids and liquids are fundamentally communal. That picture of electrons belonging solely to one atom, it breaks down. Their wave functions reach out, they overlap, they merge, forming these delocalized states that span many, many atoms. And this isn't just some minor tweak, it fundamentally defines the material's properties. Electrical, optical, magnetic, thermal. It all stems from this collective quantum behavior. And yeah, superposition plays a role too. An electron doesn't always have a definite single location within these extended states.
So connecting back, the LCAO idea we started with for molecules, it really is the same fundamental principle behind band formation in solids. just scaled up massively.
In essence, yes. LCAO describes how atomic orbitals combine. In a molecule, you combine get a few molecular orbitals. In a solid, you combine an enormous number, Avogadro's number practically.
Yeah.
And due to the sheer number and the repeating structure, those combinations result in energy levels so close together they form continuous bands. So band theory is really the LCAO principle applied to a periodic, essentially infinite system. The wave functions are still combinations of atomic orbitals, but they become these blotch functions spreading everywhere.
That really ties it together nicely. Okay, let's reinforce the metallic bonding idea again. Beyond the basic sea of electrons, what advanced concepts help understand exactly how those electrons move? You mentioned the Fermi surface.
Right. The electron sea is the concept, but the band structure, EK, gives the detailed map of allowed energies versus momentum. The Fermi surface is then a crucial boundary on that map.
Boundary between.
Between the occupied electron states and the unoccupied ones at absolute zero temperature. Its shape and size, determined by the band structure and how many valence electrons there are, tells you a huge amount.
Like what?
Like how the metal conducts electricity, how it responds to heat, to magnetic fields. Many key electronic properties are dictated by the electrons right near this Fermi surface because they're the ones available to move and react. So it gives a much more precise picture than just a sea.
Okay, so Fermi surface gives the details. And for the systems in graphene and organics, besides the mathematic idea, you mentioned Dirac electrons. Are there specific models used there?
Yeah, for conjugated systems, there are models like Huckel theory, which is a simplified way to calculate the electron energy levels. For graphene and other solids, the type binding model, which we'll get to, is often used.
Yeah.
It focuses specifically on how electrons hop between adjacent atomic orbitals, like those p orbitals in graphene. And yeah, the Dirac cone, that linear E versus K relationship in graphene, that comes directly out of applying these kinds of models to its specific honeycomb structure and orbital overlap. It predicts that massless behavior.
And we talked about superconductivity's macroscopic quantum state. Are there other exotic states driven by extended orbitals in a similar way?
Well, topological insulators, as we discussed, derive their surface states from the bulk orbital structure. But there's also a whole zoo of phenomena in what are called strongly correlated electron systems.
Only correlate.
Yeah, systems where the simple picture of electrons moving independently breaks down because the interactions between electrons become really important. These interactions, acting on electrons in potentially delocalized orbitals, can lead to really complex collective states, things like high-temperature superconductivity, which is still not fully understood.
Yeah.
Weird magnetic ordering, states where charge and spin separate. It gets very complex, all stemming from electrons interacting within these extended orbital frameworks.
Wow. Okay, this is getting deep. Let's touch on some of that advanced theory mentioned in the sources. First up, Bloch's theorem. You mentioned an equation. What's the core idea there in simple terms?
Okay, Bloch's theorem is like the bedrock for understanding electrons in crystals. It basically says if you have a perfectly repeating crystal structure, the wave function for an electron moving in it has a very specific form. It's always a combination of two parts. One part is a simple plane wave, like E dot Brown. That part represents an electron wave moving freely through space with a certain momentum.
Okay, like a free particle wave.
Kind of, but it's multiplied by another part, a function usually called U-car, which has the same periodicity as the crystal lattice itself. This U-car modulates the plane wave, reflecting how the electron interacts with the atoms within each repeating unit cell.
So the overall wave function is a traveling wave, but it's sort of patterned by the crystal structure.
Exactly. It mathematically captures the idea that the electron is delocalized, the plane wave part, but still feels the influence of the repeating atomic arrangement, the periodic part. It proves electrons exist as these extended waves in crystals.
And how does that theorem lead directly to the band structure, that EK map we talked about? How does that tell us if it's a conductor or insulator?
Well, when you solve the fundamental quantum equation, the Schrödinger equation, for an electron in that periodic crystal potential, Bloch's theorem tells you the form of the solutions. You find that solutions only exist for certain energies for each allowed crystal momentum K.
So not all energies are allowed.
No. For a given K, you get a set of allowed energies. As you vary K, these allowed energies trace out the bands, EK. That's the band structure.
Okay.
And as we discussed, whether those bands overlap or if there's a gap between the filled valence band and the empty conduction band determines the material type. Conductors have overlap or partially filled bands, allowing easy electron movement. Insulators have a big gap. Semiconductors have a small gap. Graphene's unique linear EK, EVFK, is just one specific example of a band structure derived this way.
Okay, that connects Bloch's theorem to the bands. Now, you also mentioned the tight binding approximation and its equation, some epsilon ICI plus some Langle TIJ. DIJ to a day? Can you break that down? What are epsilon EOG and...
Sure, the tight binding model is a different, often simpler way to think about bands. It starts from the atomic orbitals. The first part, with epsilon E, just represents the energy an electron would have if it were sitting in an atomic orbital on site I, all by itself. Epsilon E is the on-site energy. The C dagger and ecta jock are just fancy math operators for adding or removing an electron there.
Okay, the energy on the atom. What's the second part with TIJ?
That's the really important part for delocalization. It describes electrons hopping between adjacent atomic sites I and J. The parameter TIJ is the hopping integral or hopping parameter.
And what does it represent physically?
It represents the strength of the quantum mechanical connection, basically the overlap between the orbital on-site I and the orbital on-site J. A bigger TIJ means it's easier for an electron to hop between those two atoms.
Ah, so that's how the wave function spreads, through these hops.
Yeah, exactly. The model explicitly includes the possibility of electrons moving from atom to atom via this hopping term, TIG. By considering all possible hops between neighbors, you can build up a picture of how the initially localized atomic orbitals combine and spread out to form the delocalized Bloch states and the energy bands across the whole lattice. It directly models the extension of orbitals.
Makes sense. Finally, let's talk quantum coherence and many-body effects. How do electron interactions complicate this picture of orbital delocalization?
Right. So far, we've mostly talked as if electrons ignore each other, apart from obeying the Pauli exclusion principle. But they are charged particles, they repel each other. These electron interactions, these many-body effects, can be really important.
How do they affect delocalization?
They can sometimes enhance localization, trying to keep electrons apart, or they can mediate complex collective behaviors. Quantum coherence is key here, the idea that quantum states maintain their phase relationships. In superconductors, the BCS theory describes how an effective attraction between electrons, mediated by lattice vibrations, leads to Cooper pairs. The superconducting state, described by that complicated wave function pi plus VO wrangle, is a prime example of a macroscopic coherent state built from these interacting paired electrons extending across the material.
So interactions actually create that extreme delocalized state.
In that case, yes, they drive the formation of the coherent Cooper pair condensate. Similarly, in topological states, interactions can play a role, and the state itself is characterized by things like the Chern number, d diluat I in Bath Cal F Pei DK way, which reflects a global property of the wave functions across the whole momentum space, the Brillouin zone, BZ, influenced by orbital interactions and symmetries. So interactions add a whole layer of richness and complexity on top of the basic orbital overlap picture.
It's truly astonishing. I mean, it really comes back to that idea you started with, this surprising interconnectedness at the quantum level. It's almost hard to believe that, the solid stuff around us, its properties, come from this incredibly dynamic quantum dance of electrons spreading way beyond their home atoms.
Absolutely. And it's not just, abstract physics. Understanding this is how we design better materials, more efficient solar cells, faster computer chips, exploring things like quantum computers or better batteries. It all relies on getting a handle on these extended quantum orbitals. The deeper we understand how to manipulate them, the more we can engineer materials with precisely the properties we need. The potential is enormous.
Which really leads me to a final thought for everyone listening. Given how deeply interconnected electrons really are inside materials, how their quantum existence stretches out, what completely new things might become possible if we could get even more precise control over these extended orbitals. What technologies that seem like science fiction now might actually be within reach if we could truly master this quantum interconnectedness?
That's a fantastic question to ponder. Really fires the imagination.
Well, thank you so much for taking this really deep dive with us today into the world of quantum orbitals and materials. It's been fascinating.
It's been my pleasure. It's a topic I find endlessly fascinating too.
I think the key takeaway, hopefully, for everyone listening is just that electrons inside materials, they're not loners. They form these extended quantum states, and that dictates pretty much everything about how a material behaves.
Right. It completely changes how you should think about the solid stuff around us. It's all quantum mechanics in action on a massive scale.
Definitely. And we really encourage you, if any specific part caught your interest, Superconductors, graphene, topological materials dive deeper. It's a huge field with tons happening.
Absolutely. And it feels safe to say that the future of technology is going to be deeply, deeply tied to how well we continue to understand and eventually control these amazing extended quantum orbitals.